Have you ever been in a moving elevator or a speeding car and wondered how fast are we speeding up or slowing down? That's where the velocity-time graph comes into the picture. In this graph, time is always taken on the horizontal axis, that's the x-axis, while velocity is plotted on the vertical axis, the y-axis. Now remember, velocity isn't just about speed. It's a vector quantity. That means it has both magnitude and direction. So, a positive velocity means the body is moving away from its starting point. A negative velocity? That's the body heading back towards where it came from. From this simple plot of how velocity changes with time, we can unlock two incredibly useful things: acceleration and displacement. The slope of the graph gives us acceleration, and the area under the curve gives us displacement. Let's explore both. Now let's understand how we get displacement from this graph. There's a golden rule here. Displacement equals the area under the velocity-time graph. So if we multiply velocity by time, just like length into breadth, we get a rectangle's area, and that area tells us how far the object has moved. Positive areas, the ones above the x-axis, show movement away from the starting point. Negative areas below the x-axis show movement back toward it. And the total displacement? It's the positive area minus the negative area, including their signs. But if we only care about the total distance traveled, we just take the absolute value, add up all the areas without signs. Take a look at the figure. As you'll see, each segment of motion maps to a geometric shape: triangle, trapezium, or rectangle, all measurable. Next up, acceleration. From the graph, acceleration is just the slope of the line. In simple terms, slope is how steep the line is. And mathematically, it's acceleration equals, open bracket, final velocity minus initial velocity, close bracket, divided by time interval. If the slope is a straight rising line, we have uniform acceleration. If it's a horizontal line that's a zero slope, the velocity remains constant. So, acceleration is zero. And if the line slopes downward, we call that negative slope. The object is slowing down. That's what we call retardation or deceleration. Refer to figure 2.12. You'll see how different slopes tell us different acceleration stories in motion. Let's take the simplest case first, uniform velocity. If the object is moving with a constant speed in a straight line, the graph will be a flat line parallel to the x-axis. Why? Because the velocity isn't changing over time, so slope is zero, and that means acceleration is also zero. But remember, even with zero acceleration, the object still covers distance. So, displacement equals velocity into time, which is just the area of the rectangle under the line. Check out figure 2.13. 4 meters per second for 5 seconds gives a clean displacement of 20 meters. Simple and neat. Now things get more dynamic. If the object's speed is increasing steadily, the graph becomes an inclined straight line rising from left to right. That's uniform acceleration. For example, in figure 2.14, velocity goes from 0 to 80 meters per second in 8 seconds. The acceleration is the slope. 80 minus 0 divided by 8 equals 10 meters per second squared. On the flip side, if the object slows down steadily, the graph slopes downwards. That's uniform retardation. In figure 2.15, the velocity drops from 40 to 0 in 4 seconds. So, acceleration equals 0 minus 40 divided by 4 equals negative 10 meters per second squared. So here, slope is not just direction, it's the acceleration itself. Sometimes, an object doesn't start from rest, it's already moving. In that case, the velocity-time graph doesn't start at the origin. Instead, it begins somewhere above the x-axis, showing the initial velocity. If the object then accelerates uniformly, the line inclines upwards. To find displacement here, we calculate the area of a trapezium. The formula is 1/2 into sum of parallel sides into height. And acceleration is again the slope of the line, change in velocity, divided by change in time. Look at figure 2.16. The car starts at 10 meters per second and accelerates to 35 in 5 seconds. So, acceleration equals 35 minus 10 divided by 5, which is 5 meters per second squared. And displacement? It comes out to 112.5 meters using the trapezium area. Now let's study vertical motion, free fall, and rise. Imagine a ball dropped from a height. It gains velocity as it falls due to gravity. That's downward motion, and the graph slopes positively. But when it bounces back up, velocity decreases. That's upward motion, shown with a negative slope. The graph in figure 2.17 shows both. Line AB for falling, line CD for rising. In each segment, we can calculate acceleration from the slope and distance from the area. In AB, acceleration equals 50 minus 0 divided by 5 is 10 meters per second squared. In CD, acceleration equals 0 minus 50 divided by 5 is negative 10 meters per second squared. That's gravity doing its job, first speeding it up, then slowing it down in the opposite direction. Let's wrap up what we've learned about velocity time graphs. A straight line parallel to the x-axis shows uniform velocity, slope 0. An inclined straight line means uniform acceleration or retardation. Slope gives the value. If the graph curves, acceleration is non-uniform, changing with time. To find displacement, calculate the area under the graph using rectangle, triangle, or trapezium formulas. To find acceleration, compute the slope, that is, change in velocity divided by time, and always remember the beauty of these graphs is that they turn motion into a picture that speaks volumes. I hope you now feel confident in reading and interpreting velocity time graphs. In our next session, we'll explore acceleration time graphs and their connection to motion. Until then, keep thinking like a physicist. See you soon.